This problem says find delta y, where y is x cubed minus 3x squared plus x minus 4. So it's a cubic function. And the x value that we care about is -1. And the delta x value is 0.1, positive 0.1. First of all, what kind of problem is this? What does it want from us? Well, we probably can figure out that delta y is talking about the change in y of the function. And we've been given the change in x. So let's just draw a piece of a function. The actual function probably looks some kind of cubic equation, but let's say that around x equals 1, in the neighborhood of x equals 1, the function's curving up, we can just suppose. And let's say that we care about moving in the positive x direction 0.0. Did I make sure I said x equals -1? And so going 0.1 in the positive direction from -1, then this point right here would be x equals -0.9. So you see this delta is 0.1. And what does it want us to find out? The change in y value of the function. Let's say that the function's, by the time it got to this x value, its y value was right here. So this is the delta y. And what two things do we need to know to be able to figure out this? We need to know what the value of the function is here and what the value of the function is right here. And we know what the value of x of the function is right here. It's -1. So we need to know y of -1 for this spot right here. And for this value, what is the y value? What is the x value for this one? It's right there. It's -0.9. So if we can find out these two things, we can find out what the change in y value is. So what it is to find the delta y, we want to find the y of x that we care about plus the delta, and then we subtract the y value of the original x. So in this problem, we want to find the y value of -0.9, and then we want to subtract the y value of -1. So let's plug in -0.9 into this function, find the value, and then subtract from that what the function gives when we plug in -1. And so plugging in these values, y of -0.9, the function's value was -8.059, and at y equals -1, the value of the function was -9. Here's the tiny sketch. So we want to know what's the difference between -8.059 and -9. The difference, the delta y, was 0.941. And so the way we solved this, because when it wants delta y, it wants to know the difference in y values of the function between a point and a point in the x direction and a delta added to or subtracted if that's negative. So you find the function's value at those 2 points and find the difference, and that'll tell you what the delta y is. And this problem says use differentials to approximate the change in f of x from a to b, where f of x is 4x to the 5th minus 6x to the 4th plus 3x squared minus 5. And a is 1 and b is 1.03. I drew a lot on the board here. Now I'm going to go through it here. Let's say that this orange line represents the actual function. Okay, I don't know if this function looks like this at any particular point. Possibly. Let's say that this is the point with the value x and f of x. And then as the function's x value increments, the value of the function increases to this point, which we'll call x plus delta x, comma, f of x plus delta x. There are 2 different notations here, depending on if you're talking about a point moving on the actual function, or if you want to talk about a point moving on a tangent line that is tangent to the function at this point, f comma x comma f of x. So first let's talk about the actual function and the point moving on the function. Typically you use the symbol delta x to represent the amount in the x direction you moved along the function. And then the difference between vertical or in the y-axis from when you were at this point to where on the y-axis you are at this point is called delta y. And delta y is just the difference in y value. So it's f of x plus delta x minus f of x. This would be the actual change because you're moving on the function itself. But this problem wants you to find an approximate value by not having to calculate this function at 1.03 and then subtracting the value of the function at 1. And as we'll see, for very small values of the change in x direction, the tangent gets closer and closer to the secant line, which is the point between 2 points on the function. So now let's talk about this green line where the notation used is usually dy and dx. Now you see how I wrote delta x equals dx? So I'm saying whether you're moving along the function or whether you're moving along the tangent line, we're saying if you move that same distance in the x direction, whether you were on the function or on the tangent line. But now we're talking about the tangent line. So as you're moving in the x direction, if you were moving along this straight line whose slope was equal to the value of the derivative of the function at this x value, if you were moving along the tangent line with slope equal to f prime of x, then after you had moved dx, difference in the x direction, then you would be at this point. And if you wanted to know how much is this change in y, this differential in y, this would be the difference between this point's y value minus this point's y value. But instead of calculating 2 points and subtracting the difference, when we find the value of the derivative at this point, what we've got is the slope of this line. So this say horizontal distance is known because we picked it, it would be 0.03. So if you have the run of a right triangle and you have the slope, then to find the difference in height, you don't need two height values. You can just say the run times the slope, right? So dy equals dx times the slope, which would be m, but we're calling the slope equal to the value of the derivative of the function at this value. So this is usually easier to compute than this, especially as the functions get more complicated, because you don't have to find the value at 2 points and take the difference. You get the function's derivative and you multiply it by the run right there. So for smaller and smaller values, as this distance decreases, then the differential becomes closer and closer to the increment on the actual difference in y value. So let's do this. Do you know the techniques such as the power rule to calculate what's the derivative of this function? We know the sums and differences. We know we can take each one of these individually. 4x to the fifth, the derivative 5 times 4 is 20. X to the, we decrease it by 1. Okay, minus 4 times 6 is 24. X, decrement that 4 to a 3. The derivative of 3x squared is 2 times 3 is 6x, and the derivative of a constant is 0. So if we want to find the slope of the tangent line at 1, we just plug in 1 for every x. So it's 20 minus 24, negative 4. Negative 4 plus 6 is 2. So we can say f prime of 1 equals 2. And you remember the equation to use? Times dx. What's the dx if we're going from 1 to 1.03? We've just moved 0.03 in the positive x direction. So the value of the slope is 2. The value of the differential in the x direction was 0.3. So the approximate change in y value, the y differential, is 2 times 0.03 equals 0.6. That's approximately how much the function's value has changed between its x values changing from 1 to 1.03. Now, as this number got closer and closer to this one, this technique of differential as an approximation gets closer and closer to the actual change, and it's a lot faster, as you can see, than plugging in 1.03 to this function and subtracting the value with 1 plugged into this function. So the answer was 0.6. This problem starts out with Newton's law of gravitation, and here we have two masses that are separated by some distance s, and there's a force of gravitation, there's a force of attraction between them due to gravity. It says that the attraction force due to gravity F as a function of the distance between the two particles is g times m1 times m2, which are constants, over s squared, where s is the distance between them. And then the problem states, it says if s, the distance between the two particles, is 20 centimeters, approximate the change in s ds that will increase the force of attraction F by 20%. So we're doing to approximations. So we need to figure out how to use this information about this function to do a differential, to use the change in F. We're not talking about how much we change this, how much does this change. We're saying we know how much this changed, so we're going to have to work it around to figure out how much must this have changed, because this is the independent variable. You know, how much force there is depends on the distance between them. So think about this before we go into it. Here's a diagram that might help if you haven't already started by drawing a picture, which is a good strategy. Okay, so we're saying that we know this point right here has some distance between them, and the force between them is some value. We're saying that we want to know how much closer we got to get them so that the force between them, which increases the closer they get, we're saying this increased by 20%. So what must this have been? And remember, since we want to use an approximation, are we talking about finding the actual value here and moving along the function? Or are we talking about finding the tangent line at this point and finding knowing what the differential value is? That brings up another question. We're given that we want to check 20%. So since we're never going to actually solve the function, doesn't it make sense to say, okay, let's say that since we're working with the tangent line, let's let our tangent differential value be the 20%. Let's try to put that together. Also think about, why did I write df over f is 0.2? See if you agree with this. First of all, I rewrote this function for the force as this, which is the same thing, gm1 m2 times s to the minus 2. And since we knew that with differentials you work with the derivative of the function at its value, I found out that the derivative is, the slope of the tangent line is gm1 m2 times minus 2 s to the minus 3. And let's bear in mind what that means. That means the slope of this tangent line. And what is ds? It's talking about the amount of distance that we closed the two particles together on. So that's like the run of this right triangle. The value of the derivative at this value of s, 20 centimeters, is the slope. and the differential change in force between them is the rise. So you got the slope times the run equals the rise. But remember, we aren't talking about knowing the value in newtons. We only know a percent change that the force changed by. So what do we do next? Well, as I wrote earlier over here, we're saying that the change in force was 20% of the original force. So we divide through by F, and the value of F is this. So I set this equal to 0.2, and I simplify this. Let's simplify this. Pause the video and see if you can do that. And if I didn't make any algebraic errors, we're talking about the ratio dF over F being 0.2, and this, we're canceling out the GM1, M2 on the top and bottom. We've got the -2. S to the -3rd divided by S to the -2nd is S to the -1st. So now we've got ds right here. And remember, we know the value of S is 20. So we're saying 0.2 equals -2 divided by 20 ds. Solve for ds, see what you get. And so multiplying 0.2 times 20 divided by -2, I get ds is -2 centimeters, which means that the two mass particles got closer by 2 centimeters, which led to a percent increase of force between them of 20%. This problem says let S equal f of t, which is equal to 1 over 2 minus t squared, and find ds. And then use ds to approximate the change in S if t changes from 1 to 1.02. And so we're working with differentials, because ds is a differential. Is S the dependent or independent variable in this situation? Does S depend on t, or does t depend on S? S changes as a result of t changing. So if we were to draw a diagram right here, a picture, and obviously this function is non-linear, but since we're talking about differentials, which have to do with tangent lines, I'm just trying to look in advance and see, as t gets greater, S is going to go down. You know, I'm just imagining that the function S looks something like this, and at some point there's going to be a tangent line. So let's say that this value is some, I'm going to ignore the middle notation f of t. We know that we might as well have said s of t right here. So if the function's value at this point right here, let's say when we get to that point, we'll know that this t value that we care about, where the tangent was determined, was 1. But right now I'm keeping it abstract. So this is t and this is s. What would this distance be, this change in t? What would you call that? And we're talking differentials right here. This would be dt, right? What would this change be called? If we're moving along the tangent line, this would be that ds we want. And do you remember what is the slope of the tangent line? that would be right, because the function was f of t, so the slope of this tangent line, the one that we're going to end up caring about, is 1. So do you remember, this is the rise, this is the run, this is the slope. Rise equals what times what? It's equal to the run. Let me write nicely. Run times slope, right? What is the run in this problem? Let's say we're talking about from getting from here to here. That would be our dt times our slope. The slope is the slope of the tangent line, the value of the derivative at t equals 1. The value of the derivative f prime of t at t equals 1. So go ahead and pause the video if you want to. Let's find the derivative function of f of t. Let's find f prime of t if f of t is 1 over 2 minus t squared. So using the quotient rule right here to find f of t, you remember it's the lower function times the derivative of the higher function minus the higher function times the derivative of the lower function, all divided by the lower function squared. So for this, it would be 2 minus t squared times the derivative of 1 is 0, minus 1 times the derivative of this, using the power rule and knowing the sums and differences of functions. This turns out to be 2t over 2 minus t squared squared. So now let's find the derivative, the value of the derivative at 1. What is f prime of 1? Plug in 1 right here. We've got 2 over 2 minus 1 squared is 1 squared. So 2 over 1 squared equals 2. Okay. Did I mess anything up right here? Check your answer, see if that looks right. Yes, I reasoned it out with myself. The function is increasing. This function is increasing at the value of 1. So now we know the slope is 2, and we said t changed from 1 to 1.02. So what is dt? It's the difference between 1 and 1.02, 0.02. And this right here is ds, the differential change in s. This is very easy because now we know the slope and we know the run. So we know 2 times 0.02, 0.04. That's the change in s if t changes from 1 to 1.02 using the differential approximation, 0.04.